Good afternoon. My name is Dale Brosius. I am the Chief Commercialization Officer for IACMI, and welcome to the May 2025 edition of Innovation Insights. I'm glad to have you here today. We've got a lot to talk about. But first off, I'll start with a couple of slides about IACMI. I do this every month where I talk about IACMI's value offering to members, which flows around the terms of convene, connect, and catalyze, bringing folks together, putting them with folks who have needs and folks who have solutions, and then making things happen, whether that's a project, training, consulting, interns, use of certain facilities, just expertise that one needs, or the co-funding and networking meetings that we do have. If you're not a member already, become an IACMI member. And you do that by going to iacmi.org/members. That will be in the I'll have Kim put that into the chat as well. So just a note here about our members meeting coming up next month, June 24th to 26th in Dayton. You're going to see a lot more on this with Mark's presentation as a second presentation. So I'm not going to go into big details here, but it is our 10th anniversary and it's going to be a real blowout. Looking forward to having all our members there. Prior to that, though, next week, SAMPI here in Indianapolis, where I live. May 19th to 22nd. So that'll be a good show. It's right in the heart of the Midwest, and it's the week before the Indy 500 happens. So for those going to SAMPI, stay over for the Indy 500. You can get double dip on that. We will be in booth M15, so come see IACMI there. We've also got a couple of other things that we're doing at SAMPI. The Spotlight Theater, again, in recognition of our 10th anniversary. My IACMI impact story, and these are being told by our members in little 5-minute vignettes on a couple of days at the show. So on May 20th, Tuesday for a half an hour, or a little over half an hour, and May 21st, Wednesday for 25 minutes. So you'll get to hear from these speakers talking about their IACMI experience on the show floor. And then on Wednesday afternoon, IACMI is leading a 3-hour session on smart manufacturing and composites. So when you start to take things like digital twins, artificial intelligence, machine learning, Industry 4.0, there's all these terms out there. How do they all come together? And what are those tools that we can use to increase our ability to manufacture composites more smartly? So this session is open to all SAMPI attendees. So if you're only there walking the show floor, or you're an exhibitor, you don't need a full conference badge to be able to attend this. So I in conjunction with Dan Coughlin from ORNL, will be moderating and facilitating it. We've got 5 great panelists covering some of these topics, giving real life examples of where they're being used in industry today or being developed. So this is Innovation Insights. This is the 41st episode since May of 2021 when we launched this during the pandemic. We've featured over 115 IACMI members and partners over the course of that time. All of these are recorded and stored on the IACMI website. So you can go there and see any of these and watch the hour there. Or, if you've got some colleagues and you see something today that you'd like to pass along or have seen something in the past, send them a link to the website and they can catch up there. We will not have a webinar in June due to our IACMI members meeting. It's a typical practice is to skip June when we have everybody together. But in July, August, and September, all of those are already scheduled. And while we've got some speakers, there are presenter slots still available. Just a reminder that you don't have to be an IACMI member to attend Innovation Insights, but you do have to be an IACMI member to be able to present Innovation Insights. So before I bring Chris Oberste, our first speaker, to the screen, I just want to thank everyone who's attended these over the years. As most people know, I am stepping down as the Chief Commercialization Officer of IACMI at the end of June, and somebody else will be taking the role of this moderation over starting in July. So I've been very pleased to have done this for all these years, and I've learned an awful lot along the way. So without further ado, I will turn the mic over to Chris Oberste, who's the president and founder of Weave 3D. As soon as I can get to.
Thank you, Dale.
All right.
You should be able to see my slides now.
Sure do.
Perfect.
Looks good.
Appreciate it, Dan. So as Dale mentioned, I'm the founder and chief engineer here at Weave 3D. Weave 3D is an advanced manufacturing company that is focused on scaling up composites for high rate automotive and constructions type applications. But the topic that I'm going to talk about today is how to design hybrid metamaterial composites. So this is the idea that we can make materials that don't exist conventionally through structural engineering of different material designs. I'll start by giving you guys a little bit of background on what metamaterials are and how they are different from what you might normally be familiar with. And then I'll go through a couple of case studies towards the end here, showcasing two different approaches for how metamaterials can be applied to a solution. So just a little bit about Weave 3D. If you guys haven't heard about us, we did win a number of awards last year as for a project that we did for an automotive beltline stiffener. That's one of the case studies I'll talk about today. But we're a spin-out technology company from Georgia Tech. I did my PhD there, graduated in 2017 in the material science department. We spun the company out at that point, and fundamentally our technology is focused around this concept we call rebar for plastics, which is kind of our little trademark for what we call these metamaterials that we are developing. And the goal here is to produce a cost-effective, scalable, and locally tunable composite lattice material that is suitable for mass production. So if you've never heard of a structural metamaterial before, the definitions I've pulled up here are some pretty common ones you might find across the internet. Fundamentally, they are rationally designed, which means that we are intentionally creating these properties, artificial materials or structures of precise geometrical arrangements, leading to unusual physical and mechanical properties. So this is kind of where the metamaterial part of this comes in, is these are generally not properties that you would be able to get from conventional metal or plastic or even a natural material. They have some sort of engineered component to them that gives them something a little extra. So these materials are not just material properties, they're not constituent purely from the constituent material that makes up the actual finished product, but they're actually a function of the meso or microstructure. So what we're talking about is like things in the millimeters to tens of millimeters scale, maybe all the way down to tenths of a millimeter or smaller. You may have seen these in the news in the past, things like negative Poisson's ratio foams, so-called auxetic foams that actually, when you stretch them, they get bigger in every direction. And when you compress them, they get smaller in every direction. Whereas a conventional material, when you stretch it, it gets narrower in the other direction. And when you compress it, it gets wider. There's also things like periodic microstructures, which is material patterns that on their own, if they're just cast or extruded in one standard process, they have a generic property. But if you then produce them in sort of a foaming application or other sort of microstructures, 3D printing does a lot of this with some of the micro printed porosity. You get different properties. But the one that I'm really going to talk about today is what we call infinite mechanical tunability. So this is the idea that I can take some handful of materials, and by changing their structural interactions, I can change the mechanical properties of the resulting hybrid composite. So what kind of differentiates a metamaterial from a traditional composite is that you cannot simplify a metamaterial down to a microscale unit cell. So if you think traditional composites, the composite property is a function of the fiber and the polymer, and you can kind of slice that ratio down to a minimum size, which represents the ideal micro unit cell of that composite. Metamaterials don't really let you do that. You have to test a metamaterial at the component or coupon level, depending on how large the structures are that are involved, and only then do you see their properties. If you cut them any smaller than that, you actually only start to see the properties of the individual materials that make up the metamaterial. So just to kind of give you some foundational background here, what most people would call a normal part design would be something with a isotropic material that is homogeneous, sheet metal, injection molded plastic. You're going to pick your material. You're going to assign thickness to the part. That could be constant thickness like sheet metal, or you can have ribbing like you would in an injection molded part. You then determine, does this pass the load case that it needs to pass? And then if it doesn't, you decide, is it small deviation or a big deviation? If it's a small deviation, you maybe just need to play with the thicknesses a little bit more. But if it's a big deviation, now you might need to go to a different material. So this is, I started with polypropylene. Now I need to decide, oh no, it needs to actually be polyamide. Or I started with aluminum, but I need it to be stiffer, so I need to switch it to steel. So this is kind of that standard design loop. You basically have two variables, but you usually pick the material first, and then you play around with the thickness to get kind of the fine tuning. When we talk about composites, it's a little bit more complicated. So we have the ply materials. So you can have different types of plies in your composite stack up. You could have glass, carbon fiber, Kevlar, what have you. You also will have fiber orientations. So if you're dealing with a unidirectional or even a woven fabric, whether or not you're laying it down in the 0 direction or plus or minus 30, plus or minus 45, those will all have an effect on the mechanical performance. And then you're going to have your ply stack. So how many plies do you put in a given location? Do you have a constant thickness over the whole part, or do you have extra reinforcement in certain areas? So those are kind of your three variables in that use case. You see, does it pass the load case? If there's significant deviation, you might change your ply stack if it's not very significant, or you might actually have to go back and change your fiber orientations completely if it is significant. So this is, again, not super complicated. You can kind of still do this in a linear incremental process. But once you get to metamaterials, it becomes more of a challenge. So in the metamaterial space, you generally have a bulk material. So one of the good examples of metamaterials is injection overmolded composites. So you might be familiar with taking a piece of organo sheet, sticking it into an injection molding process, injecting ribs or other structures onto the back of that. That injection molded material is what we would call the bulk. You're going to decide how much bulk you're going to use and where you're going to put it. So this is the thickness and the location. At the same time, kind of in parallel, you're going to decide what composites are you going to put in this design. So, is this going to be a constant thickness laminate? Is it going to be something like what we do, which is lattice structures? You're then going to have to determine what are the fiber orientations and how much do you put of composite in each area. So, if you have a total part thickness of 3 millimeters, do you do 2 millimeters of composite and 1 millimeter of bulk, or do you do it the other way around? And then that resulting stack up of the composite and the bulk will give you your final part thickness and part geometry, and then you'll test the load case. The problem is, because you have all these different variables that kind of influence each other, you kind of have to go back to the beginning to redesign this part. You can't just tweak one or two variables very easily because they're very closely coupled. So changing the total amount of bulk thickness in one area also changes the local density of the fibers for the composite portion of the structure. So this is what we talk about when we talk about metamaterials, is there's a complicated relationship between the material properties and the structure that those materials are applied to and how they are distributed within that geometry that you're producing. So you might be asking yourself, okay, why use metamaterials if they're complicated? Well, the easy answer is that traditional materials are kind of limited in their range of available properties. So you might have a specific grade of polypropylene or a specific grade of steel, and then you might have similar grades or different families of grades of that material that give you a range of properties. So the chart you're seeing here is specific strength on the x-axis, specific stiffness on the y-axis, but even though you might have the option to pick a couple different grades, your properties are still going to kind of cluster around certain values inherent to that material. Where metamaterials really come into their own is the fact that you can now create really broad structural mechanical relationships. So if I make a metamaterial that consists of polypropylene and glass fiber unidirectional tapes and carbon fiber unidirectional tapes, by combining those different materials, I can tune my properties anywhere from the bulk polypropylene property all the way up to the high performance composite properties and anywhere in between. And I can kind of trade those off depending on, do I want to optimize for cost or weight or what other property? So the idea here is it's kind of the juice is worth the squeeze. You can do a lot more with a metamaterial than you can with just individual traditional materials. So the metamaterial that we're going to be talking about today is the Weave 3D composite lattice. I'm going to use this as kind of an example throughout the rest of the case studies that I'm going to talk through. But I want to point out that you don't have to use a lattice structure like this to produce a metamaterial and get these same properties. You can do this with tape laying. You can even do this with organosheet, though you tend to have a little bit less tunability. But kind of our special sauce, as it will, is we have this ability to tune these lattices within a given layer. So we can effectively make a metamaterial even in one ply, if you want to think about it that way, by putting different types of materials. So we can have glass and carbon fiber, or we can change the spacing. So you can kind of see in this graphic, the tapes are not equally spaced throughout the structure. In one direction, they are equally. In one direction, they are not equally. That gives us the ability to bias the properties and also to make the properties different in one area from another area. But fundamentally, in order to make this commercially viable, you have to be able to be compatible with existing molding processes. So the way this works is we take a tape material, we weave it, convert it into this lattice structure. The lattice goes through either a conversion, one or more conversion steps, and then goes into a part manufacturing process, injection molding or thermocompression forming. And then the resulting product is a hybrid. So it has a bulk material, it has a lattice structure, which is the composite material. And by tuning the different ratios of those materials within the part, you change the properties and you get that metamaterial behavior. So talking through these case studies, I'm going to present two different ones. The one on the left here is for an automotive beltline stiffener. This is a door component, a structural door component. It was originally designed out of carbon fiber PA6 organosheet. Our goal was to redesign this into polypropylene with lattice reinforcement and be able to match the side impact load case and maintain the existing tooling geometry. So we had to use the same part features, the same thickness, all that sort of stuff. The one on the right, this is a non-structural interior door component. The goal for this one was to start from a 1,700 grams per square meter natural fiber polypropylene non-woven mat and reduce the density of that mat to get weight savings while still complying with certain deflection constraints and again, maintaining the part geometry so they didn't have to change the overall door assembly. So unrelated parts, two different doors, two different vehicles. But what I'm going to show you here is depending on how you combine the same lattice solutions, you can get very different performance outcomes. So just a couple pictures here. The one on the left is, again, that belt line. That's the thing with the red arrow pointing at it. Similarly, the one on the right with the yellow graphic that has the red arrow pointing at it, that's the door insert. These are both part of larger assemblies. But we're only going to be optimizing the actual component level itself. So the way we start with all of this is we look at base load cases. So we're going to determine that this belt line is going to be fixed on the left and right A and B pillars. It's going to have a load applied similar to a side crash pull test in the middle of the structure. And the overall design has to be able to withstand about 490 MPa max stress in the cross section of this part. On the right-hand side, it's a little bit different. We're still going to be fixing the perimeter of this part this time, but we're going to actually apply 150 newtons at 3 distinct locations, and we have to be within a certain deflection limit at each of those locations to make this pass. So when we do a baseline simulation, this is again using the organo sheet for the beltline stiffener and using that natural fiber nonwoven for the door insert. The baseline lets us understand where are the locations of high and low stress in this part, purely based on where that part's geometry is dictating the stresses will be. So your beltline stiffener, you can clearly see there's more deflection. That's the bottom image in that mid zone. Very little deflection towards the edges where it's fixed. That makes sense. But the stresses are actually not evenly distributed. So you can see we have some gradient of stress up and down. That's the top image. But again, because we're fixing the A and B pillar, there's no stresses in those locations. So we don't need to carry that much load. On the door insert, that one is actually going to have those 3 distinct loads applied. So they have 3 distinct spots that need to be able to withstand stress and limit the deflection. So we're looking at both how much stress there is and then how much deflection is induced in this part. So flipping briefly over to the beltline stiffener itself, we ended up going through a number of design iterations here. We came up with 2 different designs that actually have the same amount of glass and carbon fiber in them, but that glass and carbon fiber is structured differently. So in the design 7 that you see on the left, the lattice is produced with a striping effect of glass and carbon fiber above and below each other. And you can actually see this in that graphic that I've put on the right here with the lamination image. So you can see there's 2 different colors of black. The more matte black color is the carbon fiber reinforced tape, and the darker black color is the glass fiber reinforced tape with a black polypropylene. And you can see that we've actually tailored this lattice so that we have a lot of material in the middle. And you can see that in this bottom image where I've laid one of the trimmed parts over an untrimmed piece. You can see where the high density region aligns with that middle region of the trimmed part right here. And then towards the edges where we're either going to trim material off or where it's only going to be the A or B pillar, we've decreased the density in order to get our cost optimization to where we want it to be. But even if you look at these 2 different designs, alternating stripes versus stacked stripes, so this is carbon fiber on the inside, then a layer of glass on the outside, the stress distributions on these 2 parts are very different. And this is because where you put the reinforcement in these metamaterials is as important as what reinforcement you put in them. On the other side, when we look at the door insert, we have 2 different designs that we came up with. So again, starting with the 1,700 grams per square meter natural fiber nonwoven, we have reduced that to a 1,200 grams per square meter with lattice. So you can see we have a high density region aligned with this high stress point here. And then we have additional tapes kind of adding some extra stiffness as we move away from that. And then we went even farther and we went to a 1,000 grams per square meter. So in this particular one, the region 8 and region 9 reinforcements are basically the same as the 1,200 GSM, but we've added an extra tape in region 10 because there was a little bit of extra deflection here that we needed to be able to reduce to get this to within its target. So talking about the actual metamaterial properties. So if I start on the beltline stiffener, the original baseline material is a homogeneous organo sheet. It is anisotropic. It has different properties, whether you're on the 090 or you're on the plus or minus 45s. However, those properties are the same throughout the material. You're not putting a different type of material in different locations. So it has a flex modulus of about 39 and a density of about 1.58. When we go to the low density lattice, where we had the wide spacing between the tapes, we're only getting a modulus of about 9.6, and we're only using glass and polypropylene to do that. This is also a 2-sided design, so the lattice is on both top and bottom of that sheet that you saw. But the density is really low. It's about 1.19. And then when we go to a hybrid glass and carbon fiber 2-sided, we now are back up at 39. So the idea being that in the area where we need the performance, we are directly matching the original organo sheet. But in the areas where we don't need the performance, we can reduce that density, save cost, save weight. And even then, we're still at 1.26 despite matching the original organo sheet. On the door insert, that one is actually starting much lower. These natural fiber nonwovens are not structural, so they only have a modulus of about 4.8. The 1000 GSM with a low density lattice pattern is about 4.5. But it's also a fair bit thinner. So it's about 92% of the original 1700 GSM's thickness. That's partly just because of how they compression mold it. They don't compress it 100% to its minimum size, so it's not quite the ratio of the weight reduction, but the density still goes down. And then when we look at the 1200 GSM version, slightly higher, 5.3, still 0.76, less than the original 1700 GSM. And then when we go to the mid-density version, we get to 6.3. So the key thing here is that these are all glass natural fiber nonwoven. So natural fiber nonwoven mat, glass polypropylene lattice. All we're changing is how much lattice is in that given region. And you can see you can basically tune that to whatever you'd like, from the single-digit GPAs all the way up about like the belt line into 40, 50 GPA. So just looking at the final results for these case studies, the beltline stiffener saw about a 50% reduction in cost compared to the organo sheet, partly because of our ability to reduce the trim waste that was had to be cut off this part. They were throwing away a lot of expensive carbon fiber, but we also got about a 23% weight savings because we were able to have a lower density structure. Compared to a steel version that was developed in a previous generation, the estimated weight savings was between 60 and 70%. And then on the door insert application, we started with the 700 GSM version, going to 1200 GSM with lattice. We saved about 15% on weight, and going to the 1000 GSM with lattice, we saved about 25% on weight. And then I like to point out this one just so people can kind of understand why do you want this, kind of unusual, non-symmetrical pattern on this structure. Well, if you were to just apply an evenly spaced lattice reinforcement over the entire surface, your cost factor would be about double what we're able to achieve with just putting the lattice in the particular locations where it's supposed to be. So this is really a very cost-effective approach to applying these materials, and it's leveraging that metamaterial property. So that is my last slide. If you guys would like to learn more, you're welcome to reach out to us at info@weave3d.com. We're happy to talk, anything automotive or any other applications that you may be interested in.
Yeah, thanks, Chris. It's always interesting to to hear you describe this. It's like you talk about it like it's falling off a log, but I know it's a lot more science into that. Are you able to take apart and fully simulate it now, or how much of this is still a bit empirical?
Yeah, no, that's actually been one of our big accomplishments over the last few years, and what drove the Beltline Stiffener Award that we got last year. This design that we came up with was fully driven by simulation. We used small scale panels to validate the simulation kind of as we went along. But the final design was fully simulated, and we validated that simulation on a component level test after we manufactured the parts, and it has good correlation. So this has been something that we've been working on with Altair for the last couple of years. And depending on how complex the part is, and whether it's a static or a dynamic simulation, we've actually been able to develop a couple of different techniques that each have their own specific advantages for certain use cases.
So when you mold this, you have to obviously, do you have to preheat the lattice like you would in an organo sheet?
It depends on the process. So yeah, if you're doing injection overmolding, that is the recommended route that we would advise. Is you preheat the lattice, you place it into the tool, and then the injection molding then final forms it and gets it to the right geometry. With the thermoforming approach for some of these materials, what we actually find works best is if you either tack or fully laminate the lattice onto your sheet that you're starting from, and then you just co-form them together. So for the case of the door insert, this is actually one where the non-woven mat comes unconsolidated. It's just kind of like a felt material. And all you have to do
Right.
is use a little bit of heat tack to attach the lattice to the surface in the right spot. And then you just stick the non-woven felt into a contact oven like you would normally, and it heats them both up together, melts them, and consolidates them into each other. And then you stick it into the press and it forms it into the final shape.
Yeah. So the natural fibers is just a needle punch mat
Exactly.
combination of fiber and polypropylene.
Hmm.
Okay. Um, and anybody in the audience, feel free to chip in and ask a question here. But what's the risk of injection molding of distortion or pushing the how do you fixture the lattice in the mold such that it doesn't get moved out of the way or out of the desired position?
That's a great question. So that is one of the key challenges when you're looking at injection molding versus compression molding. Compression molding is much simpler from that regards because you oftentimes have a carrier material and you're not flowing as much when you're actually compressing that part. With injection molding, it partly comes down to how you gate the part. So edge gating is going to be more aggressive than center gating or other types of through thickness injection. But usually we are relying on tooling features in the tool to pin or tension the lattice during the forming process. This is also one of those things where in certain geometries, if there's not a lot of complexity, you might actually prefer not to heat the lattice in order to keep
Mhm.
it more intact during the injection process. Because
Sure.
of how thin these lattices are, the injection molding step actually very quickly heats up the polymer on the surface. So you don't really have to get the lattice hot in order to get good adhesion, but you're more doing that to get it to drape or conform to the tool if you need a complex shape to be produced.
Okay. And my last question, and then I'll get to the one in the Q&A panel, is clearly you're placing the lattice on one side of the part, and so it's not a symmetrical part. How do you account for possible distortion, warpage, because of that, being a way, a long way away from what we classically call a midplane,
Mhm.
um, um, after it cools down?
It depends a lot on the material. In the case of the beltline stiffener, this part here on the left, we used an unreinforced polypropylene for the base bulk material.
Mhm.
And because of that, and because of how much shrinkage polypropylene has, this part cannot be produced with lattice on only one side. It actually has to have lattice on both sides
Okay.
to get the symmetrical behavior. With something like the natural fiber nonwoven mats, the fiber content and the fiber length is high enough that even though the lattice is only on one side, if you think about it, the actual total volume fraction of lattice in this part is still relatively small. And the natural fiber nonwoven is actually able to kind of balance out the lattice's induced warpage that you would normally see in a asymmetrical laminate. It's not going to be 100%, so you kind of do have to kind of design that in, but it is something that we can simulate in many of these components. So if we know what the CTE is of the material, we can kind of calculate how much windage that part needs to compensate for in the tooling.
Okay. Question from one of the attendees. Is there a limitation to the geometry you can create, considering the ability or lack thereof for the material to stretch? In other words, things like minimum radii,
Mhm.
depth of forming, and so forth.
So this is actually something that we're hoping to be presenting at the member meeting in June. We've been doing a project with another IACMI member looking at deep draw of a different type of natural fiber nonwoven. And in that use case, we were actually able to get about 4 inches, a little bit, maybe a little bit more than 4 inches of depth of draw. And even though the lattice itself does not stretch, the fact that you have these openings of the tapes, they can actually change their angle. So you get some relief of the forming behavior through angle opening of the tapes. So they don't stay 0-90. They actually, end up larger than 90 degrees in some cases if they're pulled over a large radius. But it's something that we actually think about in the design. So in certain areas of a part where you might have a very complex shape where there is nowhere for that lattice to go, we might intentionally reduce the density in that corner, for example, to be able to give it some relief to move. Whereas in areas where we know that there won't be a whole lot of forming in two axes or other biaxial problems, we can use more lattice in a denser configuration. So we're almost kind of doing the performance optimization first, then looking at the manufacturability and tweaking the lattice design around manufacturing process limitations.
Okay, thanks, Chris. Appreciate that. And with that, we need to move along the program to Mark Morrison. So if anybody does continue to have questions, please put them in the chat or in Q&A, and then Chris will monitor that and answer those for you.
Absolutely.
So
Thank you.
thanks again, Chris. Mark Morrison is our Vice President of Communications and Outreach, and he's going to share with us
all right, thanks,
highlights
Dale.
of our upcoming members meeting next month.
Yeah,
over to
thanks,
you, Mark.
Dale. I appreciate it. And Chris, really enjoyed your presentation. Thank you so much. And as Chris mentioned, you'll be able to hear more about a project, the resource pool project that he's working on with others at the members meeting in June. So want to share a few updates regarding the members meeting coming up in June. It'll be in Dayton. As Dale mentioned, we are celebrating our 10th anniversary at IACMI. We were announced in January of 2015, and we had a really neat press release with a lot of the impact numbers in there that's on our website that we released in January 9th. And then our meeting coming up on the 24th and through 26th is almost to the date when IACMI held its first members meeting, June 17th, 2015. And at that meeting, Craig Blue, IACMI's first CEO, signed the agreement with DOE, and IACMI literally became open for business. There were hundreds of composite experts from the industry there, government, academia, in Knoxville with the launch of IACMI. And so the signing ceremony literally took place almost 10 years to the date to our members meeting. Since that time, IACMI, this will be the 17th IACMI members meeting. We held two during COVID pandemic that were virtual, but all of those others have been in person. And really, the IACMI members meeting is a proven formula if you look at the composites industry collaboration and technology advancement. So since 2015, our member meetings have brought together 4,500 plus participants from all facets of the composite industry. I know that Dale has certainly attended every members meeting, and then we've got a few others on here. I saw Joe Fox and is on that has also attended. So bottom line is it's a major milestone for us, and but also it's a time to kind of share the impact that IACMI's had. So one of the things that we'll be providing at the members meeting will be a report, a review of a decade of innovation, looking at our impact. This is just a few shots of our quick view, but you'll see that it'll focus on everything from technical innovation, workforce, leverage, resourcing, and a lot of others. In the words of Joe Fox, we're going to tell a lot of have a lot of stats, and we're going to tell a lot of stories. So it's something we're excited to share at the members meeting. As I mentioned, the members meeting is June 24th, 26th. It's in Dayton. And if you look at, we're pleased to have Jobs Ohio as our presenting sponsor. But again, we're looking forward to being at Dayton. And Kim Hooden is going to put the registration link in the chat. So if you've not already registered, please take time to do that. Why are we going to Ohio? Well, Ohio is one of our core founding partners, certainly Jobs Ohio and University of Dayton Research Institute. As you can see, we've got leverage resources that we use there at UDRI. Brian Rice, Distinguished Research Engineer at UDRI, is one of our technical area directors and working group leaders. And you can see that we've got a number of IACMI members that have presence in Ohio. So we're very pleased to be headed back to Ohio next month. The event will be hosted at the Marriott at the University of Dayton. If you've been to a member meeting in Dayton before, you're going to be familiar with the hotel. It is totally updated, looks really nice. We've got several networking areas that are going to be, the hotel is, you're going to be able to leverage those spots. Again, it's a really neat spot and an ideal location for an IACMI members meeting. We are planning on kicking it off after the working groups that start on Tuesday that evening with a welcome mixer, kind of a networking event. This was very successful last year. We did it in Indiana, and our workforce development partners who work with ACE and Metal wanted to come in and provide this opportunity again for networking as we arrive. So that'll be held in the courtyard there at the hotel. And then one of the premier things that have been come to known for the members meetings is the networking event, normally on that Wednesday night. So we're pleased to share that we secured the National Museum of the U.S. Air Force. It's not only huge, but it's full of really cool and neat things that I think you're going to really enjoy. You see some of the images here, but we're very, very pleased that we're going to be able to offer this. Not only have a great venue, but it allows more networking engagement for our members in a relaxed setting. So this is a high-level look at the members meeting. In a minute, I'll show you the link where you can go to and you can see the detailed agenda, which is on the website. But I do want to point out, if you're going to be traveling to Dayton earlier than the members meeting, that weekend before the Dayton Air Show is happening the 21st and 22nd. But I won't go through all this. You're able to see that Tuesday we'll kick off with our 4 working group meetings. Concurrently, we've got some ACE and Metal workforce partners that are there. If you're not familiar with these programs, you'll get to learn more about them. We're pleased working with Brian Rice, going to be able to go to the Dayton Composites Center to tour, and Brian's worked with Joby Aviation to have the simulator there. It's going to be pretty neat too. So looking forward to that at the Dayton Composites Center. I already mentioned the welcome mixer, and then I won't go through Tuesday and Wednesday, but you see we have our main sessions, and then we wrap up on Thursday with a half-day session. So just wanted to give you a high-level idea of what the flow looks like. Featured speakers, we're very pleased to have what we feel is a very high caliber lineup. We've got Lou Herkman from DOE, and Mr. Berkman oversees a $3.2 billion budget for EERE, and so we're anxious to have him speak to the members and engage with our members too. Jennifer Fielding, Chief of Ceramics branch at the AFRL. Pleased to have her speak. She's going to be not only speaking, but she's going to also lead a panel for us. Mike Molnar from NIST. Mike heads up the Office of Advanced Manufacturing for NIST, and he's going to talk about the 10-year impact that not only ACME, but the other 18 Manufacturing USA institutes have had. And then Jeff Sloan, just certainly a familiar face to ACME and to all of you. And Jeff's going to be speaking with Dale during an interesting conversation they're going to have on Thursday. I'll talk more about that in a minute. We are planning on having an OEM panel. You can kind of see the lineup that we have. Again, Dr. Fielding will be moderating it, and you can see that we're pleased to have a lineup of participants from Anduril, Airbus, Joby Aviation, and Northrop Grumman. We're also going to have a very strong supply chain resiliency panel. Many of you know Dustin Davis. Dustin's going to be moderating this panel, and you can kind of see the lineup that we have too, not just aviation, but folks that are involved in everything from automotive to recreation, sports, and beyond aviation. And a nod to Brian Rice for helping us line up a lot of these top speakers. As I mentioned on Thursday, Jeff Sloan is going to lead a conversation. He's going to lead it with Dale Brosius. Dale, we hate that this is your last Innovation Insights. Kind of catches me by surprise when you say that. But bottom line, for those that know Dale and followed him in Composites world, he had a column for a number of years called Perspectives and provocations. So Jeff and Dale going to have a conversation, going to talk about not only some of the things in the past, but what about trends in the future, and then take questions from our members. So we mentioned the working group meetings. We kicked those off on Tuesday. I've got 4 meetings on Tuesday. And then Thursday morning, we'll kick the day off with a high rate aerial structures and fabrications members meeting, working group meeting. And what I wanted to point out again, if you've not already registered, or if you have registered, you can go to our website, IACMI.org, and at the very top of the page, you're going to see register for the members meeting. Even if you've already registered, you can click on that button and it'll take you to a site on the left. And the reason I pointed out is because in the upper right, you know, you can explore more about the agenda, the speakers, certainly sponsors, any other details, but certainly register for the event if you've not already. So just wanted to make sure that you knew there is a way to navigate to our website. And then Kim again has put the link in the chat. One thing that we're pretty excited about this year, that if you've been at members meetings in the past early on, one of the things that that was done is that we had a facilitated networking activity. This one we're calling a roundtable, but literally on Wednesday, June the 25th in the afternoon, we're going to have a session that's going to allow members and attendees to learn more about topics that may be of a specific interest to them. You see those over here on the right. And really it's going to allow our members new, plus those that have been at every member meeting and along the way, but able to interact with subject matter experts. So shout out to Kevin Line with Rise Building Products. He's been working with Dale and Kim Hooden and Alyssa about what are things that our members may have questions about. What are things that they're going to want to learn more about? And so we're going to have these roundtables. You see the topics to the right. Won't go through them all, but it's going to allow you, I don't want to call it speed networking, but I guess I just did, but there'll be a time that you'll be able to visit different tables and talk to different experts, and then certainly network during that session. But at each table, the bullet points over here on the right, those are the topics that you're going to be able to learn more about. So for example, innovation insights. Maybe you're a member and you never presented and you want to present. You've got some new technology you'd like to talk about. Unique things that are going on with your company. So drop over to the innovation insights table and you'll be able to learn more about that. Byron Pipes in Purdue going to be having a composites AI table. I won't go through them all, but you can kind of see those as we speak. So with that said, if you've not registered, I encourage you to look at the link that Kim Hooden's put in the chat, or certainly go to IACMI.org. And at the top of the page, you'll see our registration link. So Dale, I'd be remiss to say, if I didn't say thank you for not only the foundation, not just Innovation Insights, but the foundation that you've set. For those who may be on the call and not know, Dale did announce that he's going to be retiring at the end of June. So we've got a few surprises lined up for him at the members meeting. So Dale, I would just say, watch your back.
I don't have, you know, I'm fully confident that that I will be surprised. So, all right. So a little bit shorter than normal because we had just 2 speakers today, but very, very good speakers. So if, again, if you're not a member, become one. If you are, make sure you signed up for the members meeting because it will be a good one. And I look forward to seeing all of our members there. So thanks, Chris. Thanks, Mark. And with that, we will close this edition of Innovation Insights. Have a great day, great week, everyone.
Thanks, everybody.